even though it's horribly pixelated, can somebody explain this quote-unquote math joke to me? Because there is some pretty good math in here, even though it's dumb.
Isn't it the plus c is added on because you have to, once you take the derivative of something and you have to add on to the constant or something?
Close. First of all, it's an antiderivative. I just want to make sure we have the same vocabulary. Yes. And on the surface, that's the first element that's worth mentioning. But there is a subtlety in there that you may have missed. Notice that it's the integral of Asbury, dn.
Is it because, like, you're taking the antiderivative, like, in regards to n, so like there would have been an n in front of it. So if you were to take the derivative of that, then the n would turn into a 1.
Bingo. So if, for instance, we take the antiderivative of 7 dx, what is the antiderivative of 7 dx? 7x plus c. Okay, so if there's no variable there, it's that horizontal line that becomes a function. Okay, so what Max said is perfect. Our variable here is d. That's why that dx, that dt, that dn is so important. Notice there's an a and s, a p, an I, and r, and another I. None of those are variables. Those are all constants. So all of this is a constant. And when you take the antiderivative of a constant, you get that constant with the variable after it. And then, as Allie pointed out, you got to throw the plus c in there because it's an indefinite integral. Again, dumb joke, but has a lot of math in there that's worth discussing, as we just did. Okay, now let's move on to what we're going to do today, though, which is more on the fundamental theorem of calculus. Okay. We have both parts under control, part 1 and part 2. Now we get the applications. And there's 2 applications. There's a mean value theorem, and there's an average value. Now, I know we've done the mean value theorem already. That was the mean value theorem for derivatives. This is the mean value theorem for integrals. Okay? And it goes something like this. I came up with this as a way to explain the mean value theorem for integrals. I used to just teach it traditionally with, here's a formula, go memorize it, and just puke it back at me. But I think this example helps some people, maybe all of you, visualize exactly what we're trying to do here. So it gives you an idea of what's happening. I know you can all read, but I'll summarize for you. We've got a cylindrical glass and a bunch of ice in it. And you understand that, and you can see from the picture, that the surface of the ice is all scraggly. In fact, I think I used the word scraggly in there, if it's even a real word. As that ice melts, you all of a sudden have a glass of water. Some of the ice level will drop. Some of the ice level will come up till eventually we get this leveled surface of water. That's exactly what we're doing with integrals now. Okay? So we take this concept and we apply it to an integral problem, and hopefully this will help you understand what's going on. Okay, so I've got some function. It doesn't matter what the function is, it's just f of x. That's the red thing. Then I created my limits of integration, a and b. You can think of those limits of integration as the sides of the glass. You'll see that some of the ice is above the level of the water, and some of the ice is below the level of the water. And when it melts, it hits that water level. So f of z is our water level. How does the red area compare to the blue area? Any guesses?
Equal.
Good. They're equal. So the amount that drops is the same as the amount that rises. And we'll come back to that concept in a little while. Now, because they're equal, that line the level of the water becomes what's called an average value, or f of z. Okay, now where does z come from? I forgot to explain that. Notice, it's kind of like chicken or the egg. Which comes first? Do I have the function and then the average value, or the average value and the function? But I've got this. This is the water level here. And you'll see that the water level hits the function in two places, here and here. This would also be a z value, but I'm only going to talk about the first one. Okay, so let me get this out of the way. That z value is the x coordinate that you get from the average value. So we're kind of going backwards. We're used to doing this. We take an x value, we go up to the function, we hit the function, we come across, we get the y value. That's how we've always operated. In this particular case, I'm asking you to go backwards. I have the average value, I want to go backwards, take the y value, go backwards, hit the function, and come down to find that z value. Which is kind of contradictory to what we normally do. Okay, you think about like your algebra class and your advanced algebra, almost everything is, here's the x, what's the y? Here's the x, what's the y? How do we get the y? Now we're going backwards. Okay, so if you look at this picture, and you're going to have to remember that the red value was equal, the red area was equal to the blue area. Sorry, I had a brain fart there. We've got a nice little rectangle formed here. Okay. Looking at that picture, what's the area of that rectangle?
F of z times b minus a.
Beautiful. Would anybody like Max to explain that, or is everybody with him? I'm going to put pressure on Max. We're good? Excellent. That is an Algebra 1, maybe Algebra 2 answer. But we'd also like a calculus answer. Now, normally I would say, well, we could just take the area under the curve. Normally that wouldn't work, but what we've already talked about is the fact that the red area, which I don't know why I erased this, is equal to the blue area. Okay, so we've talked about from a calculus standpoint that the area under the curve can be found using an integral. This is a special case because the area under the curve is also the same as the rectangle. So we get that, whoops, a, b, f of x, dx. Okay, so let me give you a second to let that sink in and make sure you understand that. Both sides of this equation are doing the same thing. They're finding the area of that rectangle. Max helped us with the right side, and that was just simple geometry, base times height. The left side, however, required a little bit of explanation. It's the area under the curve, and even though the area under the curve isn't a rectangle, we can turn it into a rectangle by taking all the red area and putting it in the blue area. Because notice the blue area isn't below the curve, it's above the curve. Does that make sense? Give me a thumbs up if it's a yes. Does anybody need a further explanation?
So, is there like a mathematical reason for why the red and blue area equals 0, or are we just assuming that that's the case?
By definition, that's what our average value is.
Okay.
So we cheated and said, here's how I'm going to make my rectangle. I'm going to take this average value, and that's going to guarantee that this works. This only works, this being the bottom, only works because we have the average value. Make sense? Okay. You'll also notice, I forgot to mention this, the top of the slide says Meltdown Theorem. So a common term, and I don't know how common it is, but what I use to describe this theorem is calling it the Meltdown Theorem. I will say that you have to remember that the Meltdown Theorem is the same thing as mean value theorem. I hate to see you get to the AP test and they ask you about mean value theorem and you have no idea what it was because you just focused on the Meltdown Theorem. But the average value represents the level of the water, so as the red melts down, it'll fill in the blue and gets us this rectangle. Okay, questions so far? Now what we're going to do is we're going to play a game. We're going to take this equation and we're going to figure out, can I find f of z first or do I find f of z second? What information do I know? And then go from there. And that's a little ambiguous, but you'll see what I mean in a second. Okay, so we got that. Okay, beautiful. We're going to want to find two things about a function. We're going to find out the level of the water, the average value, f of z, but we also want to figure out where z is. Okay, so there it is. We had that already. Great. Everything's written out there. Beautiful. Matches exactly what we worked on. Great. And it's in a yellow rectangle, so it's important. But you have that already, so let's move on to an example. The average value theorem, we've pretty much pounded that into the ground, but there's a couple subtle changes here. First of all, depending on the source that you're looking at, and that source could be our textbook, it could be something you find online, it could be the AP test itself, they flip back and forth between this f of z or f average. And so I wanted you to make sure that you understand that both of those represent the same thing. It's the y value that you get from the function melting down. And you'll also notice that this equation that I have up at the top is just this, where I divided both sides by b over a. So whether you like this form or you like this form is entirely up to you. All right, so not a lot of information on here other than the fact that you need to recognize that f of z is the same thing as f of average. This will make a little bit more sense when you follow me through my example. Okay. So I did a bunch of work for you. I know that at this stage, hopefully if last night's homework went, or the other night's homework went okay, you could have done this integral problem. But that's not what this is about. It's about understanding the average value, so I did all the work for you. We'll come back to the fact that the area under the curve from 0 to 4 for x cubed is 64. And we're going to start by finding the average value of x cubed on the interval from 0 to 4. So what do we know? We have a glass that starts at 0 and ends at 4, and we have some ice that's in the shape of a cubic graph. If you are a visual learner, feel free to graph that so you can understand what we're talking about. But in essence, we have this cubic that looks something like this. We're going to set up our glass being at 0 and over here at 4. And we're going to figure out if that area under the curve, or if this glass is filled with ice, if that weird pseudo-triangle looking thing melts down, where is that melting point going to be? That gives us that f of z. If I've drawn my picture accurately enough, then this area should equal this area, just like we did in the previous example. Okay? Because the blue is above the curve, we want to fill in that part above the curve with the part under the curve, which is the red, so that we get the area of that rectangle. Okay, so that's a concept. Now, the application. Once we're done finding f of z, we're going to go backwards to find this point which is z. Okay, so before I start the mechanics, any questions on the theory here or the concept that we're going to work for? And like I said, this is a little unusual. We're not used to going from the y to get the x, but that's how we're going to do it. Okay, so how do we do that? All right, well, this I already told you. So that gives us the left-hand side of the equation. 64 is equal to f of z times 4 minus 0. Remember, 4 minus 0, b minus a, b minus a. Okay, so therefore, f of z is equal to 16. Questions? And again, for those of you that have short attention spans, f of x dx is equal to f of z times b minus a. I saved you the hassle of having to solve the left-hand side because it's right here, and therefore I plugged and chugged. I know what b is, I know what a is, I know what the integral is from a to b, and I get 16. Okay, what does that mean? That means that this value right here, even though my graph doesn't look like it, happens at 16. Good? Yes? All right. Now, here's the big question. How do I find z? If I know the y value, how do I find the x value?
Plug the y value into the equation, solve for x.
Couldn't have said it better myself. Our function is y equals x cubed. Plug 16 in for y and solve for x. That's not a nice number, is it? Can somebody fire that up on a calculator? What's the cubic root of 16?
It's 2.52.
Get 3 decimal places, AP standard.
Well, it's 198, so I'm just going to say like 20 then.
There you go. Good. Okay. Now, before I ramble about this solution, any questions? Oh, let me bring that back. There we go. Now it makes more sense. Okay. So this is actually, I got sloppy here. Hold on. Let's do this. Z cubed, z cubed, z. Okay, so if I go back to this picture, then this happens at 2.520.
Mr. Reedy?
Yo.
Are we supposed to write z as an ordered pair or just as an x value?
You can just do it as an x value. It's fine. Because notice in my problem it says find z. It's not asking you for the point. It's not asking you for this point. It's asking you 2 separate problems, which in essence, part A is saying what's the y value, and B is asking what's the x value. Does that make sense? Okay. Now, there is some strangeness that could happen. And what do I mean by strangeness? Well, it is possible that, for instance, if I go all the way back to the beginning with my first picture, clean out this mess, it is possible you could get 2 z values. I got a z value here, I got a z value here. It's also possible that you could get a lot more z values. But some of those z values might not be in the interval. So think about if we did an average value for the sine function, which this is pretty much a sine function. If this red function continues on forever and ever, this z value is going to hit in multiple spots. We only care about the z values that are inside our interval there, 0 to 4. So let's suppose you solve this. Let's suppose it was a square root problem, and I take the square root of 16 to be plus or minus 4. Let's change that. Let's say it was 9. I take the square root to be plus or minus 3. I'd have to throw the negative 3 out because it's not in the interval. We only care about where the function hits the average value inside the glass. Okay, so the physical example of the glass and the ice kind of breaks down when you go outside the glass. You don't just have ice sitting around on your counter. Okay? More so than anything, these two ideas of average value and mean value theorem, you want to use the KISS method. Don't overthink this. Rely on your pictures and rely on the idea of it being a meltdown theorem in order to be able to find that y value, which we call f of z or f average, and find the x value, which is the z value. Okey-doke? Questions? Beautiful. We did all that. Yep.